we're hoping to make this like a little interactive, so if you want to come up close, that might be better. I'll be walking around with the mic, but the idea is to definitely have some questions and answers back and forth with our panelists. Hello everyone, this is, if you're here to talk about refrigerants, you're in the right place. If not, we welcome you anyway. So today,
just do it quick.
Let's start.
Sorry, hi everyone. Brendan from NESEA from the Content Committee. Welcome to Refrigerants, Rethinking Their Role in Electrification. I'm Brendan, Ashley and I were lucky to be the two curators of this session that we're very excited about. I want to take a moment to recognize the many volunteers who have been checking you in at the door, scanning your badges and generally making the conference run smoothly. We couldn't do this without you, thank you. After this session, please fill out an evaluation and then head down to the trade show where they will be serving dessert during the next break. And I'll pass it on to Maciej.
Thank you. All right. So we all know we need to decarbonize our buildings. That's the goal right now. And how do we do that? We do that by eliminating fossil fuels in our buildings to fossil fuels combustion. So for heating and cooling, that means eliminating furnaces, boilers, and replacing them with heat pumps. For hot water, gas-fired hot water heaters, we might replace them with heat pump hot water heaters. And the goal there is to eliminate emissions locally immediately, right? So your emissions are eliminated. With time, as our grid becomes cleaner and cleaner, hopefully close to net zero by 2050, that system now doesn't have to do anything more. It just keeps getting cleaner and cleaner. But because heat pumps are the efficient way of doing this, we need refrigerants. And we've had refrigerants for a long time, and there are many different types of refrigerants. Here are just a few. Of course, we are really going to focus on refrigerants where we use the distribution in the building. There are many other applications of refrigerants that we're not talking about today, but here's just a very quick summary of refrigerants that we're going to be talking about today. So give you a run-up of what is the history of refrigerants and why are we talking about this today and what's happening. Why is this even important that we're talking about it today? So before 1930s, there were some refrigerants that were very good, like ammonia. It had zero global warming potential, zero ozone depletion potential, but it just happened to be somewhat toxic and somewhat flammable. You'll see the B2L ASHRAE classification on it. It's slightly elevated. It's not something that we can run in the buildings. Moving forward, we developed CFCs and HCFCs, the Freon era. Those were great. They were low toxicity, low flammability, but as we learned, they sort of eliminated our ozone layer and very high ozone, global warming potential. So in the late 80s, we had the Montreal Protocol, and we decided to phase out those refrigerants. Didn't mean that we stopped them, and that's it, right? You could get R22 for a very long time after this date, but we decided that, okay, we need to eliminate it, and it actually worked. It was successful. Ozone has, if we could keep the lights on, actually, that would be much appreciated. Okay. Thank you. So the ozone layer has recovered, but we still had these refrigerants that we've been using that we're all familiar with, like R451A, that have a very high global warming potential. So the Kigali Amendment was the next phase that happened in 2000s, and now, starting January 1, we're doing the next phase down for residential systems, and then starting January 1, 2026, for the VRF systems. And so what we have now are better refrigerants still. We are still low toxicity, slightly increased flammability, and we're at 700 global warming potential. That, of course, is not the best. That's why it's in yellow, but it's good because it shows improvement, and that's what we're continuing down. So this phase down, the ideas of phase down have been successful, but let's talk about what this newest phase down really means. And that's what we have the panelists today. We'll talk about the implementation and any alternative options. So today, just to give you sort of how we envision this process, We're going to have two parts. One, we'll talk about the regulatory response and the design impacts of this new phase down. What does that really mean in practice? And of course, the second part, it's nice to have refrigerants that are lower global warming potential, but it's nicer to not have as many refrigerants in the first place. And so the second part of this is to really talk about the idea of alternatives, alternative systems where we can minimize the volume of refrigerants altogether. Today, you'll see that we have a little QR code. There's a lot of background information that, as we were practicing this, we realized that there's so much we could talk about. We really didn't want to get bogged down to it. So if you look up, there's a nice summary of everything that led to where we are today. And then we'll talk about, we'll have about 20 minutes of conversation. I'll be with a mic, so if you have questions and something comes up, raise your hand, I'll come up. The idea is really to be interactive. We don't want to be just talking. And then we'll have two phases. So there are three panelists. On your right is J.S. Rancourt. He's the principal at the HTS. His company is responsible for about 30 different manufacturers, including Daikin. In the center, you have Neil Donnelly. He is the senior energy engineer at New Ecology, very much focused on hot water decarbonization, lots of hot water heat pump information. And on the right, we have the principal mechanical engineer at R.W. Sullivan. Sorry. Okay, so like I said, we'll do 20 minutes total, but please ask if no questions. The idea is we'll have questions at the end, but I do hope that we go a little bit back and forth. Okay, so with that, I'm gonna open the first discussion, and we were gonna talk about what are the impacts of the architectural designs. The big question is, do we need ventilated shafts in passive house buildings now that we have these new refrigerants? And I'm gonna hand it off to JS to start, and then we'll go from there.
Okay, perfect, thank you. So the shaft question. This is good news for us in Massachusetts and in surrounding states. We made lots of progress here, but it's not the same everywhere in the country. So the ventilated shaft discussion can be separated into two topics. Part one is, are you required to use a shaft, yes or no? Part two is, if you have a shaft, do you need to ventilate it? So part one, the shaft requirement, ASHRAE 15, the standard behind refrigeration safety, they've solved that problem as of their 2022 edition. You can use exception B, you don't need to use a shaft, you can put pipes in walls, fire rate, and not use shafts. IMC 2021 does not have that issue solved, 2024 does not, 2027 will have it solved. We're not gonna be there until 12th edition code, probably in Massachusetts, which is why the BBRS has been working on this, and there's an advisory document back in November that explains that in Massachusetts, under 10th edition code, you can use ASHRAE 15 2022 as your compliance path, which means we have solved the requirement for needing shafts. There's an exception you have to use, you have to look at it properly and design properly, but the majority of buildings will not need shafts. Part two says if you do use a shaft, as of today, under ASHRAE, it needs to be ventilated. That's going away. Addendum A and B of ASHRAE 15 2024, which was released in December, is also removing that. So eventually, even if you volunteer to use a shaft, which in some buildings you might want to, if it's a big VRF building with multiple lines, you may want to use a shaft and not fire stop at each floor. Under today's language, you'd have to ventilate that shaft naturally or with actual mechanical ventilation, but soon you won't even have to do that. So you have to be careful still. If you do use a shaft, you have to ventilate, but you are not required to use a shaft under ASHRAE 15 2022, which is good development for Massachusetts or any states like Rhode Island who allow you to use the latest safety standard to design these systems.
Yeah, and in reference to the passive house comment from Maciej, yeah, not having rated these ventilated shafts and poking so many holes in your building is very important for maintaining that tight passive house enclosure. So I think we all breathed a big sigh of relief when, this advisory finally came out from the state. So, yeah, I think the main point here is that we can do what we need to do with the new refrigerants and the new equipment that's coming off the manufacturing lines here with the A2Ls. And I think for now, we're going to recommend to our architect friends that we're using chases with fire stop at every floor instead of trying to put in dedicated shafts, even to avoid that ambiguity there with the ventilation.
One thing to watch out for on the topic of architectural design, with the new refrigerants, we often get asked what is going to change for design and in your building. So the shaft situation we've talked about, the outdoor machines are going to look the same. The indoor fan coils are going to look the same. They're going to have refrigerant detector factory mounted in it, but that's fine. We won't, it doesn't affect the impact. The branch selector boxes. So if you've done VRF, you're familiar with the branch selector boxes. Those are going to grow a little bit because they're going to have automatic shutoff valves in them. That's going to have advantages for refrigerant leaks we'll talk about in a minute, but it might get a little bit bigger. And in some applications, there's a little vent line that will need to go from the branch box to a nearby exhaust. So everything will be the same. Just talk to your engineer, give yourself some space for that branch box. When we move to new refrigerants, it'll get a little bigger, and we'll need a little vent line there. So that's the one thing to watch out for.
How does this apply to retrofits or existing systems? We installed a system 2 years ago, something breaks, or 10 years ago, we're looking at planning for a replacement. How does this new refrigerant and the new systems translate into the replacement, and what do we need to do?
JS, do you want to?
Okay,
yeah, I was going to say. More
this one.
Henry.
Yeah, sure. So under the EPA rules for these phase outs, again, if we focus on a VRF system, January 1st, 2026 is the deadline. After that, nobody can manufacture or import of R410A VRV system. Please don't wait till December 30th to try and get your R410A system. Actually, the guarantee dates are coming up the next couple coming months. After that, the only 410A that you can manufacture is for the replacement and servicing business. There is no phase out of R410A for the replacement or service business as of right now, which means you can replace and service, change parts, you can change an entire fan coil, you can change a whole condensing unit in 5 years with R410A. You can change a whole condenser and up to 75% of the indoor units. That's still considered replacement, to make sure we don't burden owners too much with forcing them to change everything. If you do want to change refrigerants, because it's 10 years down the road, or because somehow everything broke up once, whatever might be the reason, if you do want to change refrigerants, then you need to change every piece of equipment. The condenser changes, the branch box, and all the fan coils change. However, the idea is to be able to reuse the refrigerant piping. The sizes are very similar, the oils are very similar, refrigerants run the same pressure, so you want to reuse the same piping. There's some work that has to go behind it. You have to properly design it. You'll have to put in the network into the software, tell it, hey, I'm using the refrigerant, make sure that all fits, but the piping is reusable, but every component, piece of equipment does have to be replaced to do refrigerant change. R410A is not a drop-in for R32. You can't just keep the R410A fan coils and put an R32 condensing in it. So you do have to change everything, but you're not forced to. You can replace units along the way as per the rules.
Steve. And the lines that change from 410A to R32 or 454B, is that going to be the same? Will it be the same size line set?
Maciej, you just want to repeat the question?
Is the line set going to be the same length between size diameter between R32 and R451A?
Right, and this you'll learn I'm a big proponent for hydronic distribution. So just kind of echoing this same thing of when I think about the idea of reusing these line sets, to me it's always been like pitched as like, yes, we'll be able to do that, and to me I kind of equate that to like those milk cartons that have like the recyclable symbol on them, like yes, you can recycle them, like if you also like mail in $2 with it. But I'm personally wary of that.
So you guys can't say like that.
I think you'll.
We knew you'd say that, so it's okay, don't worry. So let me address the question. So when we went from R22 to R410A, the sizes changed. The pressures went up from the 300s to the 500s for the testing and all of that. That was difficult. Some of them still got reused in Europe, but that was a big change. 410 to 32 or 454B, the sizes will be almost identical. Quarter inch, half inch, up to 1.5 tons of capacity, 3/8, 5/8 above that, and the risers will look very, very similar in terms of sizes. And there's always some flexibility as well in the design. You have to adjust the refrigerant charge if you're one size up or one size below. This being said, some manufacturers are different. There's manufacturers that do a 2-pipe system, 3 pipes between the boxes. Some manufacturers do 3 pipes, so that would be tricky. Just like today, you can't throw in, I'll use the brand names, you can't throw in a Daikin system in a Mitsubishi network or vice versa. That will remain the same challenge, although there's lots of manufacturers that do both, but so that will remain a challenge. But the pipe sizes will be the same in terms of reusing it. I think it's already happening. If you have an air conditioning system at home that runs 3/8, 5/8, you can reuse that. You gotta inspect it, make sure it's in good condition, check the insulation, make sure it gets pressure tested. So you gotta do it right. Maybe send your $2, but you gotta do it right, but they can be reused, but it's not plug and play, rip it out, put it back in. It's gotta be engineered and evaluated properly.
And I think, if I understand it correctly, if your system leaks or something like that happens, the refrigerant itself, R410A, will be available for the foreseeable future, right? To reiterate, I think you mentioned that, but it's not like you all of a sudden have to replace the system if you have a leak. You can hopefully fix the leak and then recharge it with the existing unit. So that's not going away for a little while. But actually, speaking of leaks, that's a big question for me always. You know, I think we talked earlier, and you mentioned that the sort of assumed leakage rate is about 3%, plus or minus, depends, right? So every system that's installed has sort of an assumed lifetime leakage rate of 3%. So that's quite a lot, right? And then of course we have all these incidences where a system is charged, but there was a leak right at the start of construction, and we've certainly had those projects. Why isn't it working 2 months in? Because, you know, 100 pounds of refrigerant escaped. So those are exceptions, but overall there's this 3% number. So can we talk a little bit about what the new systems will have to minimize that, and is there anything else about that?
Yeah, so just to me, I always feel like there's a lack of good data on leakage rates, and it seems to be kind of swept under the rug a lot. And so the two examples for me of like recent leakage, we had our old CTO at New Ecology. He was, you know, an early adopter. He got, you know, the split system installed at his house, and then unfortunately a few years later, you know, the whole system leaks out. And so then he went through and did the math, and it came back to, he would have, if he was going to recharge the system, he would then have to run the system leak-free for another 10 years to just get back to like the same level of carbon emissions as when he was using natural gas in the house. So it's like, you know, he was trying to do the right thing, trying to get in early, and it really set him back like way further. And then the second example is just talking with a local property management company this week, and that currently this winter, like 4 out of their 5 VRF systems, like they know are leaking. A system that's brand new in the last like 5 years has already had to be recharged twice so far, and now they have like actively leaking systems that they just have to wait until this winter and like the heating season's really over to be shut down so that they can identify where those leaks are. The finger was initially pointed at dirty filters. The finger was then pointed at faulty thermostats and controls. And then, you know, finally, after just pushing through all of those things, it was like, yes, it is a leak, and we've got to wait till summer.
Yeah, I think one thing that's going to be coming, and with the new rules for the A2Ls and R32, R454B, will be onboard refrigerant leak detectors with the new equipment and safety shutoff valves at the branch boxes. So that's something that will help with isolating, like early detection and isolating of leak paths. So we're not leaking, discharging the entire charge when there's a small leak in the system at a terminal unit, which is quite often, which can happen quite often.
So a couple comments on that. That's a horror job. If somebody is refilling refrigerant in a leaking system, you got to stop the music immediately. Re-adding refrigerant is a big no-no. And you might not get heat for a bit, but you got to find it and repair it. We come across those, like stop, don't stop adding refrigerant. You got to find that leak. We do come across these disaster projects here and there, usually install-based and things not being looked at properly. Statistically, right, we look at hundreds and hundreds of projects that are out here, and that's where the statistics on leak rate kind of comes in, and your hope is that they never leak, but that can happen. With the A2L, as Tom mentioned, there's two things that are going to help with the amount that gets leaked and the emissions as a result of it. The first thing that's happening, like you mentioned, is the detectors in the fan coil. So there's a leak there, the detection will know, and it's got 30 seconds to shut an isolation valve. So even a big system that's got 100 pounds, let's say, that'd be a big system. The releasable charges are down to 3 to 4 pounds. So at least, that's limited. But then I get asked, okay, but what if the condenser, what if it leaks somewhere else? The second thing that's improving in these systems is the intelligence with all the data in determining when there's a leak. Right now, you might not get a refrigerant error until you've lost 20% of the charge, maybe 30%, depending. At that point, you get error, the system shuts down, you gotta do something about it, shut everything down, the compressor stops creating pressure, to try and stop the leak. Obviously, if nobody touches it, you might keep losing refrigerant, but you should have alarms and the system's no longer heating, so. But that's improving. With the new refrigerants, even without the sensors, they can start determining the claims now within 5%, maybe 10%. If you've lost that, the system will know, and we'll start to predict that. So there's improvements happening in trying to predict the leaks and then reduce the leaks if they happen. But VRF will still run a bit more refrigerant per ton than a chiller will, and it's still a field install system, and you're still dependent on the quality install, so you always got to carry the potential emissions risk in your calculations and comparisons. But it's going in the right direction for sure.
I think we have a question right here.
JS, you answered a bit of my question there, but I guess my understanding in the inclusion of leak detection components in the A2L equipment was primarily driven as a requirement due to the flammability and the concerns on that front. I suppose we're finding ways to leverage that for being more fine-tuned and protecting operation, and then for us, climate-concerned folks protecting just refrigerant leakage writ large. But it felt like, I guess they're getting better, but you have protection in certain places for certain things, and it still feels like that is primarily driven for combustion risks and those types of things, and not necessarily for refrigerant leakage, like climate-wise. Just curious your input on that.
Oh, you nailed it. I say it this way: the addition of refrigerant detection in the fan coils is 100%. It's a UL requirement, and sometimes an ASHRAE. It's 100% for the flammability level. It's part of the rules to allow us to run more refrigerant. It's got I call it an environmental side effect that we're happy for. It's not for that at all, but it's helping us because now the releasable charges are much lower. So the detectors help us if there's a leak in the fan coils. The intelligence around, hey, how am I running? That's for a leak anywhere. So it looks at my pressures, how come I'm here, I'm supposed to be there, and it tries to predict. I'll say the word, there's lots of AI going into the analysis of data to improve the prediction, right? That keeps improving so we can stop these systems early.
Quick question. I was just wondering, these systems have to be tested, right? They're pressure tested to, I don't know what that pressure is, 120 pounds or something like that. Where are you finding that these systems are failing? Is it failing, I'm guessing it's not in the factory tested areas. Is it that installer error? Is it somebody hits one of the lines and then it bends and you get a failure there? Or where do you, I know you can't answer every question, but where would you say most of these are coming from, and what could be done now to prevent some of these leaks from happening?
The test pressures are up to 550 or 600 psi positive, and then there's a vacuum pulled as well. So, you know, I think you see most of those failures at field joints where there's connections made in the field. So the idea with the field testing at those pressures is to hopefully to suss those out during, you know, during installation and startup. Very rare to see, you know, failures of joints or piping on factory equipment. Those are all tested in the factory before they're shipped.
I'll add some comments there. A common place is the flare joints at the indoor units. Those are flare connections, and you're supposed to, after the first year, after it goes through heating and cooling season, with the right torque wrench, you're supposed to go retighten those just once in their life, and that gets forgotten. And that's where you can eventually get a leak. That's one place that could happen. The second place can happen at the outdoor unit, at the bottom of the coil, if it's not properly elevated. The condensing units, you've seen them on stands, right? Or if the manufacturer doesn't have a proper hot gas circuit, just ice buildup and things like that. Most either have an electric resistance base pan heater, or the coil at the bottom rows are warm at all times on purpose. That's where we see what more common, or of course if renovations or things happen in the building. But we don't tend to just see it on straight piping. Brazes are extremely strong once it's past that pressure test.
Any other questions? Good.
I just wanted to make one point on this with refrigerant leaks. These systems are only as good as the installers installing them. My point in saying that is the need for training is very high. These are technically difficult to install as opposed to a legacy system that's been installed for decades. So I just want to make a comment to let everybody know that we need to push training of our workforce just as much as designs and these systems. It's great to see Greater Lawrence Tech here, bringing these kids up, teaching them. JS and I have worked at getting BRB equipment into local 537's training lab so that all our union shops are training our whole workforce. So I just wanted to make that comment to everybody that you gotta bring in the training piece, because these contractors, I mean, you kind of laid the groundwork when you said it was a thermostat or it's a, you know, they go through the list, right? They're just taking shots in the dark. We always have to answer the question, why? Why is it not functioning? But that comes down to a tech understanding what he has to look at. So I just ask everybody to really concentrate on the training piece of this too.
Okay, we're going to move on to the next section, which now, like we talked about the refrigerant, sort of the impact, what we need to change, and let's talk about the other part of it is, can we minimize the volume of refrigerants altogether? So what are the systems that are out there? What are the systems that might be something new and upcoming that, that we can point to as substitutions? So I'm going to open that up with maybe Tom, if you could talk about what you're seeing in design right now.
Great, thank you. Yeah, so what we have on the screen here shows air-to-water heat pumps. This is kind of a system that's the best of both worlds. It's bringing cold climate heat pump technology to a system where we are, instead of running refrigerant piping through the building, we're running hydronic piping. So the refrigerant is contained, you know, up at the rooftop level if the unit's not on the roof, and from there we are distributing either 2-pipe or 4-pipe chill water, hot water down to the building. So, you know, what we see from a lot of our clients and end users, they have the familiarity and want and really do a lot of times prefer hydronic distribution in their systems. So air-to-water heat pumps are a great way to give your clients and owners that kind of system, yet being fully electrified. These units are, the technology is improving every year. Right now, we are able to specify, units that can operate down to 5 degrees, 0 degrees, and still produce 130, 140 degree water at really good COPs above, 1.75 COP. So we're getting, the ability to fully decarbonize buildings with these kinds of units, which is really fantastic.
So with our focus on affordable multifamily housing, it's also been a great recommendation when we're doing, when a building's not able to go for like a full deep energy retrofit, but more of a zero over time approach. So if you have your existing hydronic distribution system, we can try to offset some of your existing boiler use by adding a air to water heat pump in there. So we have a good demonstration project currently in the works where the current rooftop chiller was reaching its end of life. So we're replacing that with an air to water heat pump, and to be taking over the majority of heating and cooling for the building. And the boilers are going to remain there to take care of any of the coldest weather, and so that we don't necessarily have to buy all of the heat pump capacity to serve the entire load. It enables you to take incremental steps towards decarbonization if that's how funding's going to work for you. You can start with one heat pump and build up capacity from there. Also big proponents because you probably know like 5 people on your street who would be able to do work on a hydronic distribution system. You're not locking yourself into a single manufacturer. I have usually said it's like, to me, like going for a VRF system is kind of like buying a Tesla. Like there's only one spot that you can go to take care of it at that point, versus like my 2013 Subaru, everyone can work on that. And so also keep with the hydronic distribution, it keeps, so you're able to phase in heat pumps over time, as long as you're designing it for a low heating water temperature. It gives you a lot of flexibility to be able to get into the air water heat pumps now, and to know that you have flexibility for whatever technology is coming down the line in the future, both for that like central heat pump unit and at the in-unit emitters. So a lot of flexibility, and we're trying to think about this idea of like when the power goes out, like having hot water through your building. We're trying to get some data on the idea of like maintaining like a warm pulse through your building. If the power's out, you still have the heat capacity of that water, and you can plan to, if you have like a boiler, that can be adding heat to your building without all of the electrical input, and so then just kind of planning on being able to pump that water around.
So some updates on the technology. A lot of these machines used to really come out of Italy, and a lot of manufacturers still come out of there, but there's more and more North American manufacturers as well that make them. The bottom picture is a modular machines. Up until 3-4 years ago, you kind of had to go the modular route to get the cold climate performance. There's advantages to that, but there's quite a cost premium for it. In the past 2 years or so, the top machine, the unitary type machines, have adopted vapor injection technology, and their performance, like Tom was mentioning, have improved. And for certain buildings, that helps with the cost challenge that these hydronic systems have. There is still a cost impact of these machines when you add in all the components, which is what sometimes makes it challenging, but we're seeing those in larger campuses, larger office commercial buildings, and we do think it'll eventually hit multi-res with larger size. There's an economy of scale of that central plant. The larger the building, the better economy of scale a mission like that works. One thing I will say is These are pretty advanced machines. The pool of contractors that can actually service and maintain these is not that big, but it will improve. But there's specific training that's required to be able to maintain and service these machines. Just like today, if you have a big centrifugal chiller in your building, you've got a pre-trained and specialized contractor for that. But of course, the rest of the building is hydronic, and that's pretty straightforward. So the technology continues to improve, and the cost is still high compared to refrigerant distribution. It's still more expensive, but the cost is improving on these air-to-water machines, and will continue to improve, we think, which is good.
I just want to throw one more thing, kind of a word of caution on existing buildings and retrofits. You are going to see, you do want to focus on a couple things. One is your, existing hot water temperature design. So a lot of buildings are, running at 160, 180, maybe even 200 degree hot water. We're really looking at a sweet spot of 130 degrees for these systems. So, you may get into needing to retrofit terminal units and coils when you're converting to air-to-water heat pumps. And the second thing too is, the load balance in existing buildings is going to tend to, to be overly, typically in a commercial building is going to be, once you size for the cooling, these units may not meet your heating load. So, you end up with more air-to-water heat pump than you need for the cooling, which is, adding to, the capital cost of the project. So as part of a renovation, I would recommend looking at envelope upgrades or upgrades to your ventilation systems to incorporate energy recovery, things like that, to help reduce your heating loads.
Okay, we're just gonna keep going unless I have any questions. Okay, so one of them is to use hydronic distribution. We just talked about that. That's one way to reduce the amount of refrigerant. Another one is packaged units. Do you guys have opinions and thoughts on packaged units?
Yeah, so these packaged terminal heat pumps, especially ones like on the right that integrate ventilation and ERVs. So you put one of these per suite. Let's think multi-res for now, which is their more common application. So advantages there is refrigerant in these. There's about the same amount of refrigerant per ton of refrigeration as a chiller, about 1.5 pounds of refrigerant per ton of heating and cooling. So they have refrigerant in it, but it is packaged, which means your leak risks are a bit lower. However, if you have 100 of these in the building, you have 100 little circuits versus the chiller, you have 1 or 2 depending circuits, but same amount of refrigerant generally. So the advantage is no more refrigerant lines, even no more ventilation shafts, which is great. Your 2 major drawbacks with these are going to be you're penetrating at each suite with approximately 8-inch ducts in and out. Need some separation between them depending on which code jurisdiction you're in. So you need to take that into account. It's doable, but in terms of your passive house envelope and just visually sometimes. So that's one thing you got to keep in mind. And the second thing is you're taking an efficiency hit here. You're trying to extract heat and reject heat through an 8-inch hole, right? You look at the SEER ratings. It's close to half what a really good chiller or VRF can do. Same with heating. There's reliance on electric heat when it gets colder. And it's not because it's great technology, we're just limited by physics here and how much of a coil area we have. We'll keep improving, but you got to think efficiency a little bit in terms of operational costs and the emissions of that over the coming years. So those are the pros and cons. Lots of interest in the market for this technology. Lots of buildings looking at it, so I think it'll become more and more popular.
Questions? Do we need to do some jumping jacks? There you go.
I'm wondering about the last air to water that you were showing. In that example, when you're doing it, let's say in a low-income housing tax credit project and it's an affordable rental, how difficult is it to do energy sub-metering on that system for individual residents to have their energy bill?
I don't think that's possible right now in the state of Massachusetts for tenant sub-metering to generate an electric or an energy bill at the moment. It's a DPH regulation. It's not really in the building code or anything. It's more of a DPH issue.
Right, I think a lot of these systems have the capability to do that, right? But not actually allowed in Massachusetts.
VRF would, but yeah, here you would have to put in BTU meters at each suite or apartment, and those themselves are very expensive. So I'm not sure. It'd be tough to work out whether that's a good payback or not. But
so would it really work only if like all the heating was included?
Yes.
Yes. Yeah.
I looked into that as far as the hydronic system, and basically the state requires you to be a public utility to do that, so it's not really feasible.
Yeah, it's a utility grade meter that they're looking for.
And then another one we were talking about is ground source heat pump. I think there's been a lot of interest in that because of the IRA. If you haven't heard, 30% of your entire system from the bottom of the well to the last emitter is now 30%. Can be counts towards the 30% tax credit. So overall, the cost of that system, first cost, is very competitive, if not actually cheaper than VRF. Of course, we don't know where that's going to end up, but right now, at least, the plan is to do that. So there's a lot of interest in geothermal. So I just wanted to see what your thoughts are on geothermal, and does that eliminate refrigerant? Is this a good pathway? What?
Yeah, it's kind of like the unicorn. It's geothermal can be used in a lot of different building applications, be it in, commercial, residential, life sciences. We're doing a study right now for a life sciences client that's looking at doing geothermal at their lab office facility out in Route 128. So, it actually is applicable to a whole host of building types. It's the unicorn if you can afford it. That's always been the drawback. It is expensive to drill the well fields, and you need the land to do it as well. So you need space and the capital to do that. One thing with the IRA, that 30% tax credit, it extends to the entire system served by the geothermal exchange field. So it goes from, you'd be able to get a credit for the wells, the pumps, the heat pumps themselves, the air handlers that are served from the heat pumps, the ductwork extending from those air handlers, and to the diffusers. So it's literally almost the entire mechanical system can count towards that credit. So, and that credit is available, I believe, even for entities that do not pay federal taxes. So it's we just went through this for a school district with their geothermal system. It was millions of dollars of tax credit. Yes.
Okay, more affordable housing questions. If you were to guess, back of envelope, with this 30% IRA money, how many individual apartments, or maybe, let's imagine it's cluster housing, right? Because maybe there's the space. The space is not the constraint. But let's think about it from like the developer's perspective on like the cost of the system install, not about the operational costs. Like how many apartments or housing units that would have just been in the regular air source heat pump dealing with this new refrigerant situation and individual systems would be like the equivalent cost of one geothermal system for multiple units with a 30% credit? Do you need like 10 units, 20 units, five apartments? You know what I'm saying? Like I'm just trying to guess like on a scale.
Yeah, the costing we've heard about from clients who have looked at it, they are seeing it about break even with VRF. So if you're doing low, affordable housing with VRF, with the tax credits and with the mass save incentive. It's nothing to sneeze at. It's $4,500 a ton for geothermal. I think with those two combined, you're on par with the cost of your ref system.
One thing that has just come up in some recent projects where we've talked about geothermal is just the need to have like balanced heating and cooling over the course of the whole year. If you think about the ground that you're on as like a thermal battery, we can't just be pumping heat out of it because then we'll eventually drop the temperature of that. So if we're pulling heat out for heating season, we've got to be recharging that with cooling. And so, on a building where we had been talking about, great, could we do heating and cooling and domestic hot water? They're like, let's start by cutting out the domestic hot water because that'll definitely, be too much heat extraction out of the ground. And so I think that's balancing those loads is part of the motivation for some networked systems with not just one type of use, but a variety of building uses that you have that load diversity, but just something to keep in mind.
Just some technology updates on geothermal systems. People think of them as, if I have geothermal, I gotta run water source heat pumps everywhere, which is common, and you can do that. You can have little 1 or 2 ton heat pumps in every suite. They each run a bit of refrigerant, and that's still an option. There's other things you can do with it though. There are centralized water source heat pump chillers that can make you hot water and chilled water loop. There's King Open School is a famous one that's geothermal that uses that if you still want to use chilled water and hot water and use regular fan coils. You can do domestic hot water, like he mentioned. So there's machines now that are meant for domestic that feed off the geo loop. There's also air source heat pump you can use to supplement the loop if you have a balance problem, and you can choose to run them when it's the right temperature outside. So that's also an option if you need to balance your loop. And finally, some projects want to use geothermal for obvious reasons that we've talked about, but they like the VRF aspect. They like having compressors kind of centralized, not in each suite. So we can do water source VRF as well as an option, which some big soldiers homes in Massachusetts are doing, in Chelsea and Holyoke, big geothermal projects. So lots of flexibility once you have a geofield for domestic heating and cooling. Even ERVs can be water source or ground source off of it. So lots of evolution in the last few years on the technology that can tack onto a geothermal system.
Forgot to mention, we are doing 2 projects that are affordable housing with geothermal right now, and this kind of goes to the tenant billing. Those are using vertical stack heat pumps in each apartment, and those heat pumps could be tied to the tenant load center, and they would pay that electric bill directly. So that would be, a nice fit if you're looking to have the tenants pay their own way for heating and cooling.
I have a couple of follow-ups. So one, you called it a unicorn system, right? I think I'm assuming it's because you meant it's like very high performance. So
yes.
So could you just talk on that? And then the second part is also the idea of balanced loads. A lot of our projects, I think, are cooling dominant. So is domestic hot water a good application for geothermal?
Yeah, so I think, the unicorn comment, there's 2 things. The condensing temperatures are much higher because you're rejecting heat to the ground and using that as a sink also is in the winter, so in the summer. And so your condensing temperatures and your COPs are much higher year-round. And so the idea that an air-to-water heat pump system may run out of steam, run out of gas at 0 degrees F, and you need some kind of auxiliary heat on the very coldest days in winter. With a geothermal system, you wouldn't run into that issue. You're always going to be, rejecting heat to that 55-degree ground. What was the second one?
Just the domestic hot water?
Oh, domestic hot water, yeah. So in a lot of buildings, especially multifamily passive house buildings, we do see that they are cooling dominant on an annual basis, and actually having that domestic hot water system tied to the geothermal can help balance the system and the field. and essentially help to reduce the gain in temperature in the well field over the summer.
Any questions on that? I know it's the end of the conference, but come on. Okay. So are there any other systems? Because we're sort of done with this. I was hoping we would have a little bit more back and forth, but okay, here we go.
You mentioned earlier about the volume of refrigerant in some of those heat pump systems, similar to chiller-based systems. Is that true for water source heat pump as well? Is there some savings on the refrigerant side? Because it's still a bunch of systems using refrigerant.
Yeah, a water source heat pump, whether it's geothermal or running off a tower boiler, will also run around 1.5 pounds of refrigerant per ton of heating and cooling. Package chilling, it's the same thing. And a chiller, even a heat pump chiller, will run 1.3 to 1.6, 1.7, so it's about the same. VRF, VRV will run anywhere from 2 to 6 if you have a big system that's like average of 3. So that's why, you know, the people say, oh, VRF will have about twice as much refrigerant just in it as other conventional systems. The other ones are kind of similar. So even a geothermal system will have about 1.5 pounds of refrigerant per ton of refrigeration, heating and cooling.
I think I heard you say 1.75 CLP for some of the water distribution systems, which seems pretty low compared to VRF. So is that like a full system efficiency including all the distribution and everything?
Yeah, so that was for air to water heat pumps at anywhere from 0 to 5 degrees outside air. So I believe most VRF systems at JS probably knows some exact numbers, but COPs are maybe slightly higher than that at 5 degrees, closer to 2.
Low to mid 2s.
Low to mid 2s, yeah. So VRF definitely has better low temperature performance than air to water heat pumps, and can stay online down to lower temperatures as well, and have ratings to negative 13 some systems, negative 22 Fahrenheit.
I got some color to it. So yeah, the VRF COBs are low to mid 2s at those temperatures. That includes the distribution and the fan coil, so that's really good. However, with a hydronic system, that's just a straight up COP looking at just the unit. When you start doing heat recovery within the system, when you start tying in heat recovery with the rest of the building, that's where your overall building COP can look pretty good. Obviously, you have to do that. You have to buy the heat recovery air source heat pump chiller, so the cost goes up. You have to have the controls and things like that. So with hydronics, you do have some flexibility, and if you have a central plant that's well controlled, you can really bump those up. So you can't just look at the COP. But yes, the ambient performance, VRF will still usually win head to head on just how good you can extract heat. You gotta look at the whole building.
Hey, just as you're running over, I do want to mention just one other type of system, kind of similar to the geothermal diagram that we have here. But the development of sanitary drain source heat pumps is something to be keeping your eye out for. That's coming along. So instead of having wells drilled into the ground, taking a section of your existing sanitary drain, stretching that out a little bit with some drain water heat recovery units, and being able to extract or reject heat to your sanitary drain. Working with the national labs, like you're not just talking about the domestic hot water that's going down your drain, but all of the water. And so there's enough water going down the drain, and there's enough energy in there to more than serve just your domestic hot water load. And you think about the temperatures that are going down your drain, you're looking at more advantageous source temperatures than geothermal. So we're looking at better COPs and not having drilling costs. So that's coming along.
I'll add some. Massachusetts plumbing board just gave approval to this technology last year for wastewater energy recovery. So looking for some sample projects out there to get started. But You do need to have a storage tank on site for it. It's going to be designed, but that's like the last. We're gonna use every BTU before we throw them out the building, right? So every air we exhaust, extract everything you can. This is another piece. All this water going down the drain. So those are we think will grow in popularity. There's also the district version of this, where as a district you can do that. You can even tap in as a building to a drain line and use that. That's allowed in most places. So we think that's going to be a growing technology. That's very interesting to try to use those BTUs.
Just a question on the few of the alternate system designs you're proposing here, and thinking of them in the context of refrigerant leakage potential. Of course, switching to a lower GWP refrigerant, check, that's great. Reducing overall refrigerant system, check, that's great. The other big advantage that I see is just reducing or eliminating field-made refrigerant connections, which I think is also a huge advantage. But I'd wondered if between the various ones you talked about, if there are still field-made refrigerant connections in those systems, and if there are preferable systems that have more packaged refrigerant components that have hydronic connections, and what the differences might be between different system approaches.
Yeah, no, good question. The only system that will have field connections would be a split type system, mini split, multi-split, VRV, VRF. Everything else that we talked about here in this section does not have field connections. It's a package system. Where things will be a little bit different, if you look out 10 years, once propane reaches North America, it's already starting in Europe. We're about 5-10 years away, depending on codes. We'd be hard pressed to see propane, because that's an awesome refrigerant, it's just propane, to see it inside a water source heat pump, inside of what, so they're gonna be contained outside. So if you do use an air to water heat pump chiller, then maybe in 10 years, 15 years, you can move to propane. The other refrigerant that's currently just used for some domestic hot water applications, some high lift applications only, CO2 is, we believe, is in Europe, it's expanding as a refrigerant even for HVAC. There was some things released just last week over in Europe, so we might be able to see that. It's a tricky refrigerant to work with, but we might be able to see that technology just looking out down the road for any of these systems, including possibly VRV and VRF.
My understanding of the tax credits at 30% previously were that they extended conservatively to the heat pump and maybe towards a buffer tank. But is the IRA now saying that distribution explicitly is included?
You'll need to consult the tax attorney, but the tax attorney that we did work with for our project, yeah, they made it clear that it extended to the entire system down to the last diffuser. It does, yeah. It's extraordinary, quite frankly.
Yeah, it's transformative if it stays.